Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we are going to continue talking about GPU programming for general purpose computing. And in particular, we are going to focus on the memory hierarchy from the software perspective and also from the hardware perspective. Together with that, we will also discuss some of the new innovations of the recently launched NVIDIA H100 architecture. So just to very briefly recap on what we covered in the previous lecture, where we started the basics of GPU programming, let me remind you that this is the recommended reading, the book, Programming Massively Parallel Processors. You can now access the 3rd edition, but very soon will be available the 4th edition with new materials and updated contents. Of course, if you want to become a let's say proficient CUDA programmer, you will have to be very familiar with all the contents of the CUDA programming guide, where you can use it as a reference for anything you decide to program in your GPU. So let's start reminding what's GPU computing. In GPU computing, what we follow is typically what we call the accelerator model. That means that the GPU is seen inside the heterogeneous system as a coprocessor or an accelerator of the CPU. And the CPU is going to offload computation to the GPU. In the most basic operation, this offloading process has 3 steps. In the first step, we transfer data from the CPU memory to the GPU memory. Then we launch a GPU kernel or a function that is executed on the GPU for execution and computing by the GPU cores. And finally, we transfer back results from the GPU memory to the CPU memory. The way to program this, the typical way to distribute computation in this program structure is to use CPU threads and GPU kernels, and we will use CPU threads to execute sequential or modestly parallel sections of the code that will run on the CPU, and massively parallel sections of the code will run on the GPU. This way, we will typically have one or only a few threads executing serial code, and at some point when we reach to those sections of the code that are massively parallel, we will launch a GPU kernel to be executed on the GPU. Observe that this GPU kernel is going to use a certain number of threads. These threads are grouped into thread blocks. After the kernel terminates, the controller returns to the CPU. Some more serial code can be executed on the CPU by the CPU thread. And at some point, we may launch a new kernel, either the same kernel because it's an iterative algorithm, or a completely different kernel using its own number of threads and threads per block. If we take a closer look at how the code looks, we'll see that in our code, we are going to have function prototypes. This will be the typical one for a function that is going to be executed on the CPU. This is the GPU kernel. Observe that we are using this global qualifier to distinguish it from a CPU function. And then inside the main function of the host, of the CPU, we will have to first allocate memory for the GPU on the GPU memory using CUDA malloc. We will later have to transfer data from the host memory to the device memory, that is from the CPU memory to the GPU memory using this CUDA main copy. We will have to decide what's the execution configuration, that is the number of blocks and the number of threads per blocks that our kernel is going to use. And finally, in the next step, we will launch the kernel. This is the typical syntax of the kernel call. Observe that here we have the execution configuration and the arguments. After the kernel terminates, we can return results from the device memory to the host memory, also using CUDA main copy. And this operation, it will be repeated as many times as needed, either to launch the same kernel or launch different kernels inside the same program. As I said before, in order to distinguish the GPU function or a GPU kernel from a CPU function, we use this global qualifier. And as we will see today, inside the GPU kernel, automatic variables are transparently assigned to registers, registers in the GPU cores. In this GPU cores, there is also a scratchpad memory called shared memory that is shared, that is accessed by all threads belonging to the same thread block. And we may eventually need to synchronize the threads that run together in the same thread block, in the same GPU core, using a specific primitive for intra-block synchronization that is called sync threads. For you to get more familiar with CUDA programming language, in this slide, you see the exact syntax to do the memory allocation with CUDA malloc, memory copy with CUDA main copy, either from host to device or from device to host. Observe that this parameter here defines what's the direction of the copy. The kernel syntax of the kernel launch with the number of blocks, the number of threads, and the input arguments, and the memory deallocation called CUDA free. In some cases, we may need to also signal the CPU when the kernel, the GPU kernel terminates its execution. To do so, we use this explicit synchronization, CUDA device synchronize. We will talk about it in later lectures. Remember that in our previous lecture, we started covering our first GPU programming example. Is vector addition, very simple thing, where we have two input arrays, A and B, and what we perform is the element-wise addition of these two arrays, A and B, to store the results in an output array C. In the most straightforward implementation, what we will do inside the GPU is assigning one GPU thread to each element-wise addition, in a way as you see on the slide. So that means that the first thread is going to compute this addition, A0 plus B0, and store the result in C0. And this is the addition that the next thread, let's say thread 1, is going to execute. And these are the additions for the rest of threads. But the whole set of threads that execute one kernel is called a grid. And one important thing to take into account here is that we have a certain number of GPU cores inside the GPU. So we need a way of assigning threads to the GPU cores. And this is why in the software hierarchy, we have something called the thread blocks. So what we do is grouping threads into blocks or thread blocks. So for example, we can consider that these 4 threads belong to the same block, block 0. These are block 1, block 2, and block 3. So in that sense, we can say that block 0 is computing this part of the vector addition, block 1, this part of the vector addition, this part block 2, and this part block 3. Remember that we also explain this code for the vector addition. This is actually the, let's say, host code. This backadd function is called by the main function executed on the host CPU. We assume as well that in this main function, we have previously allocated arrays A, B, and C in the CPU memory, in the main memory of the system, and the main function calls this backadd function. Inside this backadd function, what we do is, first of all, allocating GPU memory using CUDA malloc for A, B, and array C, and we copy the input data from the CPU memory to the GPU memory. That is array A and array B. And observe that here, the copy is performed from host to device in both cases. After computation on the GPU, we'll have to return the results, array C, from the device to the host. And finally, we will deallocate the GPU memory if we don't need to use it anymore. To perform the computation, first thing to do is deciding what's going to be the number of threads per block that we are going to use. In this case is 512. And then depending on the size of the input array, in this case n, we will need to use a certain number of thread blocks. And this is the kernel call. Backadd kernel, we are using this number of blocks, this number of threads per block, and these are the input and output arguments. One interesting thing to take into account here is that the size of the input might not always be a multiple of the number of threads per block. So in that case, what we will have to do is launching a number of threads that is the ceiling of, let's say, the ceiling of the number of blocks that we need to perform the specific computation. So we have to round up the number of thread blocks, and that's what we do, or we can do with, for example, this expression that we have here. And then inside the kernel code, because we have launched more threads than what we really need, the total number of threads is going to be probably slightly larger than this n. For every single thread, we'll have to check if we are inside bounds, and in that case, perform the vector addition or the element-wise addition in this particular case. Observe as well that the way that we assign the computation to threads is by using this index I, and we calculate this index I based on the thread index, the index of the thread inside the block index, which is the index of the block inside the whole grid of threads, and the block dimensions. We were also explaining in our previous lecture how to access, let's say, more complex data structures, for example, images that are two-dimensional data structures that have a certain height and a certain width. As you know, the way we access images typically in C programming is with this syntax here, where J determines what's the row of the that we access in the image, and I tell us the column that we are accessing. So for example, this element here, this pixel here is image 01 because it's in row 0 and column 1, or this one here is image 12 because it's in row 1 and column 2. In CUDA, same as in C programming, images and it's essentially any array is stored in row major layout. What that means is the a specific pixel image ij will be exactly stored in this position in memory, where width is the width of the image, of the two-dimensional structure in this case. So this image here is going to be stored in memory linearly, as you can see here on the slide. And observe that there is a distance between the first element of each row, that is the width, and we can call it a stride. And this element, for example, which is image 01, is exactly located in the position 0 times 8 plus 1, where 8 is the width of the image. Or this element here, image 12, is located in image 1 times 8 plus 2. By using those indices, we can access the pixels in the image. We can do that using one-dimensional thread blocks and one-dimensional grids inside the GPU, or we can also use two-dimensional grids and two-dimensional thread blocks. In that case, we are using a number of threads in the X dimension and a number of threads in the Y dimension. These are given by the built-in variables griddim X and griddim Y, as you can see on the slide. And for example, now, if we want to distribute this image among two-dimensional blocks, what we will do is assigning a two-dimensional region of the image to the different thread blocks. For example, thread block 00 is going to be working on this part of the region, and the rest of the image is assigned to other thread blocks. For example, this one here is thread block 21, block index 2, because in the X direction is in the, let's say, column 2, and in the Y direction, in the vertical direction, is in the row 1 of blocks. So that's why this one is block 21. Inside each block, we are also using the thread indices. For example, the thread that we would assign to this pixel is a thread with thread index X equal 1 and thread index Y equal 0. Why is that? Because this thread, it's in the, let's say, column 2, I mean, the second column of the thread block, that is column 1, and in the first row of the thread block, that is row 0. And now, if we want inside a GPU kernel, we want to tell each thread the specific pixel that they have to access, we'll have to calculate the row and the column of this pixel in the image. And the way to do so is by using block index, block dimension, and thread index. So for example, for the row, we calculate the specific row by using the block index that tells us where exactly in this vertical dimension we are. We multiply that by the block dimension. In this case, the block dimension in the vertical direction is 2. And then inside the thread block, we have to add the thread index y. And similarly, we calculate it for the column. Here you can see one example. For example, this pixel here belongs to, it's exactly in row 3 and in column 1. The way we calculate row 3 is by multiplying the block index y, which is 1 in this case, times the dimensions of this block in the vertical direction, which is 2, plus 1, that is the index in the y dimension, in the vertical dimension of the thread inside the thread block. So this way we can access this pixel 3.1 by using the row 3 and the column 1. So we are already familiar with threads, thread blocks, and grids, which are, let's say, the basic components of the software hierarchy of programming GPUs. There is some interesting innovation in the H100, the recently released H100 architecture, that are called the thread block clusters. One interesting observation is that in recent times, GPUs, the size of GPUs has increased, and they have more and more GPU cores. We have seen since Volta architecture that it's not surprising that most powerful GPUs have almost 100 GPU cores or even more in the A100 and the H100 GPUs. So with such a large number of GPU cores, it might make sense to add one new lever to the software hierarchy to improve execution efficiency. And this is going to provide programmers with control of locality at a granularity larger than a single thread block on a single SM. Remember that in the traditional GPU programming model that we have been explaining in the beginning of today's lecture and in our previous lecture, we have threads, we have thread blocks, and the total number of threads and thread blocks represents the grid. This is the typical software hierarchy and software organization that we have seen in all NVIDIA GPUs until the A100 GPU. The novelty in the H100 is that they add this new level in the software hierarchy that is called the thread block cluster. And as you see, this thread block cluster is clustering, grouping several thread blocks together. These thread blocks in the same cluster can synchronize and exchange data. This is very interesting because it's going to be possible, or is possible, to exchange data and communicate between threads in this thread block and threads in this thread block. That was impossible in previous generations. For example, we cannot directly communicate threads here with threads here in the A100 GPU. The thread blocks in the same cluster are guaranteed to be concurrently scheduled. This is also something really interesting, because as of today, we could not make any assumption about the execution of threads, of thread blocks. They were transparently scheduled, and the only way to synchronize them was at the very end of the execution of the GPU kernel. Yeah, so the interesting thing here in this H100 architecture is that we know that these 4 thread blocks belonging to this thread block cluster are going to be running together at the same time, maybe on the same SM or maybe on different SMs. Actually, these thread blocks in the same cluster run on the SMs within a GPU processing cluster, or GPC. If you don't know exactly what this is, you can identify these GPCs in the overview in this layout of the H100. The GPC is each of these portions of the H100 that you see. So in total, you can see that we have 8 GPCs in the H100 GPU. So threads and thread blocks running on the SMs of this GPC will have the ability to communicate, exchange data, and synchronize if they belong to the same thread block cluster. That's actually kind of interesting thing, because it allows us to create new ways of communication in our programs, and that can also save a lot of execution cycles from having to write data to the global memory for communication with other thread blocks in the system. At least in this case, by adding this new level in the hierarchy, we are going to have more, let's say, faster and an easier communication across thread blocks running on different SMs if they belong to the same GPC. So this data sharing and this communication is possible with the new SM to SM network that is now implemented inside the GPC. So we have, let's say, a new level in the software hierarchy: thread block cluster, and grid. Hopefully in future lectures, we will be able to give you more details about these thread block clusters. We are going to talk a little bit more about them today, but probably in future lectures, we will be able to even show you some programming examples. Okay, after having reminded the GPU software hierarchy, threads, thread blocks, and grids, and now thread block clusters as well, let's go to the next thing that is important to understand, to know the basics of GPU programming, and these are the GPU memories. If you take a look at the overview of the block diagram of the H100 GPU, you can already see here what's the external memory. In the particular case of this H100, it's HBM3 memory. You can see the stacks of HBM3 memory represented here with the memory controllers on this side, and on the other side of the GPU block diagram. And also here in the middle, you can see the large L2 cache that theoretically can achieve or can reach up to 60 megabytes. As far as we know, in the, let's say, first product that will be released, the size of this L2 cache will be 50 megabytes. And now if we go closer and take a look at the H100 core, we can already see here some of the memory spaces, like these L1 data cache and the shared memory. Observe that these two memories are actually sharing the same physical space of size 256 kilobytes. It's possible for programmers to partition them and decide how much of these 256 kilobytes they want to use as L1 data cache, which is hardware managed, transparently managed, doesn't need to have any programmer intervention, or the shared memory that is the scratchpad or software managed cache. We can also see here the register file. It's a pretty large register file here and here, with in total 64K 32-bit registers. And here in this slide, we have a simplified representation of the memories in the GPU architecture. Observe that on the slide, we have multiple SMs or GPU cores, and inside each SM, we have some control logic, and we have our typically called by NVIDIA CUDA cores, but these are essentially the SIMD lanes, SIMD functional units. And these SIMD functional units can access registers pretty fast in essentially one cycle. There is a register file in each GPU core or each SM, and this register file is partitioned across the different threads that are going to run on each SM or GPU core. These threads have also access to the L1 cache that is on chip near the cores, as you see, and the access is pretty fast, about 5 cycles. And also pretty fast, they can access the shared memory or a scratchpad. And also a constant cache that is typically used to store constant values, and is especially well optimized for broadcasting the access values across the threads belonging to the same warp. We will talk about the constant cache in a later lecture as well. And then outside of the chip, what we have is a global memory. In the case of the H100 are these stacks of HBM3 memory. This memory is typically DRAM, either HBM memory or GDDR memory. And the access, even though these memories these days provide higher and higher the memory bandwidth generation after generation, the latency of access to these off-chip memory is still quite high, and it might be in the order of magnitude of 500 cycles. The good thing is that the data that is accessed from global memory is cached in the L2 cache, which is much closer, is inside the chip, and they are larger and larger, as we have already seen in a previous slide. There were some architecture innovations, interesting ones in the A100 GPU already, which was launched in 2020. If we observe how data was loaded from the DRAM, from the external global memory into the shared memory in older generations like the V100 GPU and older, if we wanted to move data from DRAM to the shared memory, it was necessary for the GPU threads to generate the addresses and then issue a transaction to the DRAM, bring the data all the way through the cache hierarchy, L1, L2, L1, and then to the registers. And then from the register file, these threads could copy the data into the shared memory for later use by, for example, the tensor cores. The novelty in the A100 GPU was that by using, it was possible to use asynchronous copies between DRAM and shared memory, which would be saving all these two steps here. So bypassing L1 and bypassing RF. And this way, providing a more efficient access. Still, in this A100 GPU, the addresses of access to the DRAM needed to be calculated by the GPU threads running on the GPU cores. And that's something that has been improved even more in the H100 GPU with a new unit inside the GPU core that is called the Tensor Memory Accelerator. And here you can see the difference between what is done in the A100 architecture and what is done in the H100 architecture. In the A100 architecture, it's possible to use this asynchronous load instruction where we need to generate the addresses by the threads. We send these addresses to the global memory to perform a read, and then in an asynchronous manner, we copy the data from the global memory directly to the shared memory without having to go through L1 cache and registers. This was efficient, but even more efficient can it be if we offload all the computation of the addresses, the address generation from the conventional cores and the threads to this Tensor Memory Accelerator. So there will be one single thread sending a request to this Tensor Memory Accelerator. This Tensor Memory Accelerator generates the addresses, issues the read to the global memory, and then the transaction happens from the global memory to the shared memory. So TMA unit reduces the addressing overhead. There is needed only a single thread per warp to issue the TMA operation, and this TMA operation supports different tensor layouts from 1D to 5D. There are not many details yet about this is performed, but what we can see is that because the structure, the organization of the tensor, given its dimensionality from 1D to 5D is known in advance, it's just necessary to know one base address plus the tensor height and the tensor width. These are the parameters that I can guess that the single thread per warp is sending to the TMA unit, and inside this TMA unit is possible to calculate the exact bounds of the region that is going to be copied in every cycle. Hopefully, we will know more details about this tensor memory accelerator in the near future, and we can also discuss and explain them in these lectures. And another interesting novelty in the H100 architecture is the distributed shared memory, because now we have thread block clusters, we have different thread blocks that then can communicate to each other. It's possible for them to share data that resides in their own shared memory. And that's possible because there is now a shared memory virtual address space. So one thread block can load, store, or perform atomic operations to the shared memory of other SMs that is in use by other thread blocks. So in the A100 model and previous generations as well, if we wanted threads in one thread block communicate data to threads in another thread block, it was necessary to do this through the global memory. And maybe even it was necessary to terminate the kernel to have like a global synchronization. There are also like ways of doing it using atomic operations, and we are going to talk about them in later lectures. But let's say that the default way was using global memory and performing a global synchronization, which is essentially a kernel termination and launching a new kernel. In the H100 architecture, and thanks to this SM to SM network or GPU core to GPU core network, it's possible to move data directly from the shared memory of a thread block to the shared memory of another thread block. These thread block clusters and the distributed shared memory are leveraged by using the cooperative groups API. I haven't found yet any details about this, how this is done, but if you want to learn about these cooperative groups, you can take a look at the CUDA programming guide, because these cooperative groups or this API was already defined for previous architecture generations. I think it started in the V100 architecture. The TMA unit, the Tensor Memory Accelerator unit, also supports copies across thread blocks in a cluster. And in order to synchronize and in order for a thread block to know that one of these transactions, one of these copies is done, it's possible to use asynchronous transaction barriers. So if we go back to this picture, simplified representation of the memory hierarchy of the GPU, the novelties now in the H100 architecture are the direct copy, these from global memory to the shared memory, the asynchronous copy from global memory to shared memory that they started in the A100 architecture, but now it's even improved because we have this tensor memory accelerator to calculate addresses. And we also have this SM to SM communication, this SM to SM network inside the same GPC. In order to give you a few more interesting values here, interesting numbers here, the size of the L2 cache is 50 megabytes, and the size of the global memory is expected to be up to 80 gigabytes. So it's essentially twice as large as the global memory of the previous A100 architecture. And also the bandwidth of this global memory has greatly increased to up to 3 terabytes per second, which is really very large bandwidth. Okay, let's keep talking and let's keep discussing about details about how to use these different memory spaces inside the GPU kernels. So whenever we declare global variables like these global variables are going to be stored in registers. The compiler, the MVCC compiler, will identify these global variables and will assign them to the physical registers that we have inside the GPU core. These global variables are for use of a single thread, and the lifetime of these global variables is the lifetime of the thread. Threads can also use arrays like this local array N of certain size. In principle, these arrays are for usage of a single thread, so their lifetime is also the lifetime of the thread. But in principle, these are stored in global memory. This is something that will happen by default, but in cases where the size of this local array is known at compile time, the compiler can try or will try to allocate this array into registers. Remember as well that threads that run inside the same block can share data by using the shared memory. And the way to define what variable, when a variable or an array is in shared memory is by using this shared qualifier. Threads inside the same grid can also access data that resides in the global memory, and this global memory can directly be allocated inside the GPU kernel by using this device qualifier, or it can be allocated by using CUDA-malloc from the host processor. And finally, we have the constant memory that it can either be declared using this constant qualifier, or it can also be allocated from the host. Okay, and here you can see some simplified representation of the memory hierarchy of the CUDA programs. For each individual thread, this thread is going to have access to its own local variables that reside in the physical registers. Threads that belong to the same thread block can share data through the shared memory, this local on-chip scratchpad memory, and threads belonging to different thread blocks can access data, common data that resides either in the global memory or the constant memory. In this slide, which is an old one, we are missing the thread block cluster, but that's essentially the new level that we add. These two blocks here, for example, could belong to the same thread block cluster. In that case, these threads here could access this shared memory and vice versa. The idea of using, of having all these multiple spaces in the memory hierarchy is to take advantage of data reuse. Data reuse essentially means that some input value or some data that it's in global memory is going to be accessed more than once by either a single thread or multiple threads. If the data residing in global memory could never be reused by the same thread or other threads, we wouldn't need to use registers or shared memory or any other closer memory space. But that's not the case in common programs. We will see that it's very common and very frequent that there is a lot of data reuse, and we as programmers have to take advantage of this data reuse to improve the performance and optimize our programs. Let me give you a very brief example and very simple example for a start. This is the image that we showed in previous slide, and what we want to do in this slide is to apply a Gaussian filter to this image. The way that we apply this Gaussian filter is by applying this mask that is 3 by 3 in this specific example to all the pixels that belong to this image. For example, for this input pixel, we are going to calculate an output value that is the result of performing the convolution of this green mask with the corresponding pixels, as you can see here at the bottom in this code. But the interesting observation here is that some of these pixels are also going to be accessed by other threads computing the corresponding output value for other pixels. For example, we'll have one thread computing the output for this pixel, but we have another neighboring thread computing the output for this pixel here. And let's say the window that this thread needs to access is this window here. And if you compare both windows, they are sharing some location, right? So these 6 elements, these 6 pixels here are going to be accessed by both the thread computing this output pixel and the thread computing this output pixel. So there is a lot of data reuse here. And the way to take advantage of data reuse is by using one technique that is called tiling or blocking, that in the case of the GPU consists of loading parts of the image, in this case, tiles of the image, into the shared memory. Because the shared memory is on chip, it can be much faster accessed than going to L2 or going to the global memory. And this is how the modified code would look simplified good look for this Gaussian filter. We first need to declare the array L data that is going to keep the whole tile of the image that we are going to load to this shared memory. After loading the data into the shared memory, and observe that we are skipping the specific code here, we have to synchronize to make sure that all threads that have been loading data into shared memory are done with this operation. And after synchronizing, they can perform the convolution by using the Gaussian filter and using the data that it's now residing in the local memory, in the shared memory. These sync threads is the synchronization function, the intra-block synchronization function that synchronizes all threads in a block. What this essentially means is that you know that thread blocks are divided into warps when they are mapped onto a GPU core. So warps are executing instructions. At some point, all threads in one warp will reach the synchronization point, will reach the sync thread. After all warps have reached this sync thread, they can resume the execution and they can continue with the execution. In the case of the Gaussian filter that we have just seen, this will happen after the corresponding tile of the image is already stored in the shared memory. And using this sync thread avoids data hazards when accessing shared or global memory. That's why we need it. So this technique is called tiling or blocking. As I said, it's not only used in GPUs, it's also used in CPUs and other processors as well. It essentially consists of dividing loops, operating on arrays into computation chunks so that each chunk can hold its data in the cache or other on-chip memory. For example, the shared memory or a scratchpad in the GPUs. Using tiling or blocking avoids cache conflicts between different chunks of the computation, and essentially consists of dividing the working set so that each piece fits in the cache. We are going to first see one example for CPUs, and then we will see one example for more elaborated example for GPUs. Our example is matrix multiplication. In this slide, we see how we would perform the naive matrix multiplication, where we multiply two input matrices, A and B, and obtain an output matrix C. And we assume that the matrices, all three matrices, are stored in row major layout. So in order to calculate this C matrix, or one particular element of the C matrix, we have to go through a whole row of the matrix A and a whole column of the matrix B. And this is how our code will look like. Observe that these two outer loops are to go over all elements of the matrix C, from C00 to C n-1, n-1. And then inside this inner loop, what we are doing is going with this index K through the whole row of A and the whole column of B, performing this multiplication and accumulation operation to calculate and finally obtain the value, this Cij. But what's the problem with this code? The problem with this code is that we are not taking advantage of data locality, and this code on a CPU will have very poor performance due to poor cache locality. That is especially due to the accesses to B. Why is that? Because if you think about the accesses to A, it's perfectly fine. When we access the first element here of this row, there will be a cache miss. We'll have to go to the external of chip memory, bring a whole cache line, place it in the cache near the core, and that's perfectly fine, because for the next access for k = 1, we could be accessing this value here that is inside the same cache line. So in that case, it's perfectly fine. But that's not what happens for the accesses to B. Why is that? Because this element here belongs to one cache line that is about here, right? So when we access the next element, that element is not in the cache line that was previously brought to the closer cache when k was equal 0, because that cache line is somewhere around here. So whenever we access one element of matrix B, there will be a cache miss, and that's hurting the performance a lot. So the way of achieving better performance here by achieving better cache locality is computing on smaller tiles or blocks that fit in the cache. And these blocks can be placed in the cache of a CPU, or in the case of GPUs, can be placed in the scratchpad memory or the register file. So what we are doing is dividing the input and output matrices into these tiles. And what we will do is, first of all, loading this tile of matrix A into the cache, this tile of matrix B into the cache, and then performing the corresponding operations, multiplications and additions. And here you can see how this code would look. So we have, again, external loops to go over the whole output matrix C. We'll have to set to 0 the elements of the corresponding tile of matrix C that we are calculating, and then we go over the tiles one by one. But then inside this inner loop, we are calling another routine, another function called multiply tiles that is performing sort of matrix multiplication of these small submatrices that are the tiles of blocks. And these tiles of blocks have this size, tile dim times tile dim. So we first perform the matrix multiplication of this submatrix here and this submatrix here. Then we go to the next two tiles, this one here and this one here, and we continue doing the whole process until we complete the entire matrix A and the entire matrix B, and we keep accumulating on some temporary variables that will finally have the output results for the corresponding elements of the matrix C. If you want to learn more and revise other aspects of caches, I can recommend you this lecture on advanced caches from Professor Mudlus from spring 2021. And now, after having covered the example for CPUs, let's go and check and see how a matrix multiplication is performed, at least in a preliminary implementation is performed inside a GPU. In our case, again, C equal A times B. This is our matrix C. If we want to calculate this green element in matrix C, we'll have to go through the whole corresponding row of matrix A and the whole corresponding column of matrix B. So the way, say, straightforward parallelization and probably also providing quite good performance, the parallelization approach here is to assign one thread to each element of the output matrix, and now each thread inside the GPU kernel will have to go through the whole row of A and column of B, as we can see in the slide, in this code here. So first of all, we calculate the row and the column the same way as we saw before, based on the block index, the block dimensions, and the thread index. By using this row and this column, we access the corresponding elements of matrix A and matrix B, perform the multiplication, accumulation, and after being done with the whole row and the whole column, will have the result in this sum variable, and we'll store this result in the corresponding element of the output matrix C. Now the observation here is that there is data reuse, and what that means is that the 4 threads that we have assigned to these 4 output elements of matrix C to perform the corresponding dot product operation, all of them will have to access exactly the same elements, exactly the same row of A. And also, if you look at these 4 elements here that will be computed by other 4 threads, they also are sharing all these elements of the same column of matrix B. So there is a lot of reuse in matrix multiplication. If we don't do anything to take advantage of this data reuse, we may be lucky and sometimes find the data in the L1 cache because other threads have requested these values, this data from the global memory, and it turns out that this data is in the L1 cache, but that may not always be the case. And in some cases, we won't be lucky. So the data previously accessed by other threads has already been evicted from the L1, so it's not anymore in the L1 cache. So we'll have to go again to the global memory. So the solution, as we have seen before, is to perform use tiling or blocking, essentially divide the input matrices into different tiles that are loaded into the shared memory. And we keep them on the shared memory as much as needed, as long as needed, until we have computed the whole tile. So that's what we are going to do. We will have one thread block and the threads of this thread block computing these elements of the output matrix C. And the first thing to do in the first step is load the corresponding tiles of matrix A and of matrix B, load them into the shared memory. And after they are loaded into shared memory, we will synchronize using sync threads, all the threads computing the elements of the corresponding tile of the matrix C. And we will repeat again and again for the next tiles after we are done with the whole row and the whole column of B. And the next tile. And this is how the code looks like. First of all, we have to declare the arrays in shared memory, these tiles for A and tile for B. Then observe that we again calculate row and column based on block indices, block dimensions, and thread indices. Then we have the this outer loop to go tile by tile over the two matrices A and B. And inside the body of this outer loop, the first thing to do is to load the tiles into shared memory. Observe how here we access corresponding elements in matrix A, matrix B in global memory, and store them in the corresponding position in the shared memory. So this is collaboratively done by all threads belonging to the thread block, and that's why, depending on what's the thread index Y and thread index X of the thread, they are reading from global memory certain values of A and B and storing them in the corresponding positions in the shared memory. After these tiles are loaded, we have to use this sync thread to make sure that everything, all whole tile of A and whole tile of B are already in shared memory, and then the computation can take place. After performing this computation, computing with the tiles, we'll have again to synchronize in order to not start loading a new tile before all threads of the thread block have used the previously loaded data in the tile. So that's why we need these two sync threads in the body of the outer loop. We will talk again about matrix multiplication in a later lecture, essentially because matrix multiplication is especially important these days for, let's say, important workloads like machine learning, neural networks. So that's why we will talk about them again, and we will talk about how to optimize further this matrix multiplication in later lectures. But if you want to take a look at another explanation of this tile multiplication on GPU, I can recommend you this lecture from previous semester. And also recommend you the corresponding chapter, chapter 4, Memory and Data Locality of the Programming Massively Parallel Processors book, if you want to learn a little bit more about the GPU memory hierarchy. This is all for today from my side. Please don't hesitate to contact me if you have any questions about today's lecture or about the course in general. And I look forward to seeing you in a later lecture. Thank you very much for your attention.